Hello everyone. I'm sure you haven't missed me in the slightest, but here I am inflicting myself on you anyway. Thought it might just be helpful to give you a sort of virtual chemistry lesson from my own little office room at home here. I said hello everyone earlier, didn't I? But I should probably say hello everyone except Dragos, because you will be tuning in 2 minutes later than everyone else probably. Now, anyway, what I'm going to do is I'm going to give you a lesson on the second part of topic 4.3, the haloalkanes today, which is the content covered in topic 4.3 question sheet 2. My real aim actually is for you to finish this week all of the 4.3 content. That means 4.3 question sheets 1 and 2, mark them both. Then sit down and revise the content of topic 4.3. Then do the multiple choice questions and then put yourself under test conditions, do the 4.3 test and submit your marks via the file on Moodle titled 4.3 test submission. Whilst you're at it, can you also submit the marks for the 4.2 test that you should already have completed by now? There is, again, a file named topic 4.2 test submission on Moodle. Okay, on with the lesson. About this. No teacher. It feels complete without their own little whiteboard. I found this old mini whiteboard in the garage, used to belong to my son when he was a toddler. I dragged it in, got my board markers, my board rubber there as well. All I need. In fact, I'll show you something else. This board, I've dragged it in from the garage, comes complete with a resident spider. He was on the front of the board when I dragged it in. He's sensibly retreated to safety behind it. Can you see the little fella there? Hope he'll be all right here in the little office room. He's not missing the garage too much. Anyway, I'll keep an eye on him. Okay, I've got a number of tasks lined up for you today. Here's the first one, a little naming task. 6 compounds on here, which I want you to write the names of. Now, A to D should be straightforward enough. E and F, I'll give you quick pieces of extra information to allow you to answer those. When naming E, when you have 2 or more different halogens attached to an organic compound, you list them in alphabetical order. So bromo comes before chloro. On F, you've got a double bond and a halogen on the same compound. Now there is a big list of orders of priority of all the different organic functional groups, and this will show you which takes priority over the others when there are 2 or more functional groups in the same compound. For now, all you need to know is that the double bond takes priority over the halogen. Okay, pause the video and write the names of all 6. Resume when you think you've finished. Okay, now A should have been straightforward, 2-chloropropane. B, 1,2-dichloropropane. Hope you've put the di. If you haven't, no mark. C, 1,1-dibromoethane. Note, that was 1,1-dibromo, not 1-bromoethane. Are you allowed half a mark if you wrote 1-dibromoethane? Certainly not. This is chemistry, of course, not sociology. We don't do half marks. D is 1-chloro-2-methyl-propane. E. Said earlier, you put the bromine first. It is 1-bromo, 2,2-dichloropropane. E. Double bond takes priority. As I said, you have the double bond on carbon 1, but because you can number from either end of a compound, the chlorine would like to give itself position number 1 as well. So we have a bit of a conflict here. Double bond wins though, takes the priority. That means it is 4 chloro, but 1 in. Okay, hope you did well at that. Let's move on to the second task. I would like you to draw the structure of and name all the possible structural isomers of that compound, C4H8Cl2. Again, pause the video and resume when you think you've finished. Right, here goes. Hopefully you started in a logical place and you've done all of these in a logical sequence, and the obvious place to start is 1,1-dichlorobutane. You can then of course swiftly move on. You've got 1,2-dichloro, 1,3 and 1,4. That's exhausted all the ones. Next step would be 2,2. After that, 2,3-dichlorobutane. At that point, you've reached the end of the straight chain isomers. If you thought you had more, hopefully if you think about it, you'll realise that any additional isomers you have drawn were actually the same as one of the other ones you've already drawn. Now, we then move on to branched isomers. Now, the only place we can position a branch is, of course, on the second carbon. So all the remaining isomers are based around 2-methyl-propane. Again, let's start in a logical place. 1,1-dichloro, 2-methyl-propane. Hopefully you can all appreciate the logic of the name. Next, we have 1,2, still dichloro, 2-methyl-propane. We can also have 1,3, and at that point, that is actually it. There are 9 isomers, and you've seen them all. I wonder if some of you tried to draw additional ones, though. One possibility is that some of you might have tried to think, oh, what if I put a chlorine on the branch? Could that be a different isomer? But of course, this chlorine on the branch right here could just be considered to be on carbon 1. If we take the straight chain as being those 3 chlorines, then the branch could actually be the one at the end. So actually what you've got there is again 1,3-dichloro, 2-methyl-propane. And actually you can't put any chlorines on the branch and create new isomers, because of course you could always consider the branch to be the third carbon in the straight chain. Okay, that's the end of the second exercise. Right, the third task involves a look at this reaction, which is called the hydrolysis of haloalkanes. In this case, we've got the hydrolysis of chlorobutane. Hopefully this mechanism is familiar with you. Note how I've been careful. I've got my curly arrow coming from the lone pair of electrons on the O, unambiguously from that lone pair, going again unambiguously to the delta plus C, not vaguely in the direction of it, right to it. Other curly arrow from halfway along the line over towards the Cl. I've got my dipole as well there, and a negative charge on the OH. Now, this reaction can of course happen in a similar way with bromobutane, and one of the things which I asked you to look at was an investigation into the rates of hydrolysis of the different haloalkanes. Now, we would have actually done a practical based around this week. Obviously, those plans have been put on hold. Hopefully, we'll still do that practical at some point. But we'll simply have to sort of learn the outcome in advance of doing the practical, the opposite way to which we usually do things, of course. Anyway, which would have the higher rate of reaction? Would it be the hydrolysis of chlorobutane, or would it be the hydrolysis of bromobutane? Now, that depends on two factors, actually, which I shall show you. Okay, this reaction really happens in two stages. Firstly, the OH minus ions are attracted towards the delta plus carbon. And the stronger the attraction of the negative ions for the delta plus carbon, then the higher the rate of the reaction should be. Now, I shall show you these electronegativity values. I would like you to pause the video in a second and list the three haloalkanes, chlorobutane, bromobutane and iodobutane, in order of the size of the dipole, and then write a sentence to say which one of them would have the strongest attraction, or which one of them would have a carbon atom which would most strongly attract the OH minus ions, writing a coherent sentence or two to explain your answer, please. Pause the video and have a go at doing that, and full sentences, please, everyone. I don't want anyone starting by saying the chlorine will or the iodine will. We're not talking about chlorine or iodine, we're talking about the chlorobutane or iodobutane. So explain your answers fully, please. Okay, now hopefully you have worked out that in the chlorobutane, the difference in electronegativity between the C and the Cl is relatively large, meaning a relatively large delta plus and delta minus, or a relatively large dipole in that compound. In fact, the size of the positive charge in chlorobutane will be higher than in the other two. Obviously, iodobutane will have the weakest or smallest positive charge. So, ideally, what you have written is there is a larger difference in electronegativity between carbon and chlorine than between carbon and either of the other two halogens. This means that chlorobutane has the largest dipole, and therefore the delta plus carbon atom in chlorobutane will most strongly attract the OH minus ion. And therefore, when considering electronegativities, we would expect chlorobutane to have the highest rate of reaction. That's what I meant by a fully coherent answer. Okay. Now, moving on now, looking back at our mechanism, there is a second stage to the reaction. The hydroxide ions get attracted in to the carbon, but that's only the first step. For them to form a bond to that carbon, the C to Cl bond has to break, allowing carbon to take on an additional bond. Now, Of course, the same thing would have to happen in bromobutane as well. The C to Br bond will have to break before the OH minus ion can actually form a new covalent bond to the carbon using that lone pair of electrons. Now, we therefore need to have a look at bond enthalpies. Now, bond enthalpies really just another name for bond strengths. You've got the 3 bond enthalpies there. Again, I'd like you to pause the video in a second and write a coherent explanation using the bond enthalpies alone of which of the 3 haloalkanes would you expect to have the highest rate of reaction. Again, only considering the bond enthalpy values. Okay, I want at least 2 full sentences, please. Right, all done. Now, hopefully you found this fairly straightforward. It's a simple matter really of saying that the C to Cl bond is stronger than the other 2 bonds, but you must have written the C to Cl bond is stronger, not just the Cl bond is stronger. Cl can't form a bond with itself, it has to bond to the carbon. So the C to Cl bond is the strongest of the 3 bonds, therefore it is the most difficult bond to break, and therefore from the bond enthalpy values the iodobutane would actually be expected to have the higher rate of reaction. Now, we've got a contradiction here though. According to the electronegativity values, chlorobutane should have the higher rate of reaction. According to the bond enthalpy values, iodobutane should have the higher rate of reaction. Which factor is more important? The electronegativities, which determine the strength of the attraction of that OH minus ion for the delta plus carbon, or is it the bond enthalpies which determine how easily the C to halogen bond is broken? Which of those factors is more important? Well, the same email in which I sent you a link to this video also contains a link to another video which will show you exactly which factor is more important, and also therefore show you which of the 3 haloalkanes has the higher rate of reaction. Okay, it's the end of that part of the lesson. Okay, final part of the lesson now. Briefly explained at the end of the lesson on Friday how ozone destruction is brought about by CFCs. Just want to mention that again and then move on and look at how our ozone can also be destroyed by nitrogen monoxide and get you to compare the mechanisms of the 2 reactions. So let's quickly walk you through the steps again. Up in the stratosphere, where there are high levels of UV light, oxygen molecules, some oxygen molecules, are broken down into oxygen atoms, with the double bond being broken by the UV light. However, those oxygen atoms are highly unstable. They will quickly combine with other oxygen atoms to form ozone. The thing is, ozone itself is broken down by UV light into oxygen atoms and oxygen molecules. The reverse reaction here also happens in the presence of UV light. So actually, up in the stratosphere, you constantly have the forward and reverse reactions happening, and an equilibrium is established. Of course, if an equilibrium is established, the forward and reverse reactions are occurring at the same rate. At least they are until CFCs come along. So I mentioned that CFCs, such as this one, are broken down by UV light into 2 radicals, and with the C to Cl bond being broken. It's always the C to Cl bond that gets broken because it is weaker than the C to F bond. Now, that forms a chlorine radical. Chlorine radicals can destroy an ozone molecule according to that first step, forming a chlorine monoxide radical. The chlorine monoxide radical will then combine with oxygen atoms, and remember there are always some free oxygen atoms up in the stratosphere due to the top reaction, forming or reforming, I should say, a chlorine radical and another oxygen molecule. That chlorine radical is therefore reformed in this process and can go on to destroy more and more ozone molecules. In fact, it acts as a catalyst for the destruction of ozone, and the overall equation is that. Now, I suggested for yourselves that you look up the mechanism by which nitrogen monoxide destroys ozone. Hopefully, you found out it's that. Nitrogen monoxide, which although being a compound, is actually a radical as well, can, up in the stratosphere, remember nitrogen monoxide gets in the stratosphere due to aeroplanes, basically. It would be formed in aeroplane engines, the high temperatures at which the fuel is burned in plane engines causes nitrogen and oxygen in the air to combine, forming both nitrogen monoxide and nitrogen dioxide. Now, nitrogen monoxide can react with ozone, forming nitrogen dioxide and oxygen, and then the nitrogen dioxide reacts with oxygen atoms to reform nitrogen monoxide and oxygen. So again, the nitrogen monoxide is reformed and can go on to destroy more ozone. Now, hopefully you've already written out those two mechanisms, these two parts. In fact, the overall equation for the second mechanism is exactly the same as the overall equation for the first, except you've got NO as the catalyst. Now, the thing is, you do have to remember both these mechanisms, but it shouldn't really be a case of having to remember two entirely different mechanisms. There are several essential similarities between these two mechanisms. What I'd like you to do is write out the two mechanisms again and write out the essential similarities that exist between mechanism 1 with the chlorine free radical and mechanism 2 with the nitrogen monoxide. If you can appreciate those essential similarities, it will make it much easier to remember the two mechanisms. Okay, have a go at that. Right, one final thing. I've attached this document to the email I sent you, which had a link to this video and several other videos and a couple of Quizlets on the haloalkanes that I want you to try as well. Please, I'll try to regularly send you a few Quizlets as well from now on to keep you busy. Now, what I intend you to do with this, I would have set you this to do in class ideally, is to produce a big poster summarising the three main organic mechanisms that we have studied and the important terms associated with those. Ideally, I want this done on A3 paper. If you don't have any A3, just sellotape two A4 pieces to each other, please. And simply complete, firstly, the definition of the three key terms there and give an example of each one. For example, a radical, the example would be Cl dot. You then want the two types of bond fission defined with an example of an equation for each one. I then want the three main mechanisms written out. Methane and chlorine, copy the overall equation first and then complete the rest of the mechanism with the name of the type of bond fission and then equations for the three stages. The electrophilic addition one, again, state the type of bond fission and this time three-stage diagram required. Be really careful. As I mentioned earlier, lone pairs where necessary, dipoles where necessary, and be really precise with your curly arrows, please. Lastly, nucleophilic substitution, only a two-step diagram needed there. Yeah, but please have a go. And Grace, I want you to be nice and creative with this one. Sarah, I know you have not the slightest intention of being creative. You don't believe in that type of nonsense, do you? But at least make it colourful, Sarah. The rest of you, have a real go at it. And use this as a revision tool as well. Once you've finished with it, get it stuck on your wall. Be staring at it again and again so that these mechanisms get entrenched in your mind, and take some pride in them. Make the type of poster which I'd be happy to put on my wall. In fact, when we do return to college, I'll invite anyone who thinks they've done a really good one to bring it in, and we'll get them put up on the wall in the lab, the best one or two of them anyway. So take some pride in your work and produce a decent poster for me, please. Okay, that's all for now, everyone. Speak to you again next week. Hope you're all well. All the best now.